So my thesis is titled Modeling the Effect of Long-Wave Radiation from Solar Panels on Soil Moisture. So for a bit of background, agrivoltaics integrates photovoltaic power production, so solar panels, with agriculture in the same plot of land. So in the example that I put in my poster, here's a solar farm in Colorado where they're growing crops under solar panels to give you a visual. So it has a lot of potential because it can reduce competition for land between farmers and power companies. And the shade from the panels reduces the need for crop irrigation. But to optimize these systems, energy pathways must be characterized. We have to know how much energy is available for the plants and the system as a whole. So while solar panels shade the crops, they also emit long-wave radiation. So that's an added energy input that even though they're getting less sunlight, they're getting more long-wave radiation. So the goal of this study was to quantify that downwelling long-wave radiation at the ground surface under the solar panels. So to go through my methods, this is a flow chart kind of that says what I did when I created my code in Python. So at any given time in ground position S, we go through this whole process. So I took weather data, so that's things like humidity and air temperature, and use that to find the temperature of the solar panels. And from there, I could compute the long-wave heat flux at the ground from a little differential panel element, and then sum up the effects from all those elements to get the effect from one whole panel, and then sum up the effects from all of the panels to get the total long wave from the panels from the whole solar array. So that gives us the long wave from the panels. But then the other source of long wave energy is from the sky itself. So the air actually emits long wave radiation. And so we compute something called the view factor, which I'll get into in a bit. And we multiply that by the long wave from the sky. And this will give us the total long wave. And we can use the enthalpy of water, which is the amount of energy needed to vaporize water, to convert that amount of energy to evaporative potential, which is just saying that if all of the long wave radiation went to evaporation, how much, what depth of water would be evaporated. So the view factor, I'll zoom in a little bit more, is the portion of long wave energy from the sky that strikes the ground at a given position. So I won't get into all the details here, but you can basically imagine that if this is the ground point, the ground sees these white wedges of light and is blocked by these gray wedges. So we can multiply that fraction by the total long wave radiation from the sky to get how much from the sky it's receiving. So for the results, we can see that this is a graph just at a given time t. The gray bars is the region under the panels. So the green flat line just shows how much the control area in full sun is receiving, just the long wave energy, not the total energy. So this doesn't include sunlight. And then the orange line is the long wave radiation from the panels, and the blue line is the long wave radiation from the sky. So you can see that if we sum these two lines, the blue and the orange, that we're getting, the part under the panels is getting a lot more, significantly more long wave radiation than the control area, which is what our hypothesis was. So then if we sum all those effects across time and convert it to evaporative potential, which again is just the amount of, which is just the amount of evaporation that would occur if all of long wave radiation went to evaporation. You can see that we get anywhere from like 15 to 40 centimeters of evaporation, which is a huge amount of water. So it goes to show that long wave radiation is very significant. So for future work, this model could be used to design the panel geometry that would be needed to meet water and energy needs of a crop, or the panel geometry that would be needed to promote uniform soil moisture distribution, so that it would be easier to water your crops.